Welcome back to my channel Shri Statistics. Today we are going to be talking about another theorem which is related to this previous heading, simultaneous reduction of a pair of quadratic forms. So this theorem states that if A and B are two real symmetric matrices such that B is positive definite, then there exists a real non-singular matrix P such that P transpose AP is equal to diagonal elements of this diagonal matrix lambda 1, lambda 2, lambda n, and P transpose BP is equal to I, that is an identity matrix of order n, where lambda 1, lambda 2 and lambda n are the characteristic roots of this equation A minus lambda B equal to 0 in lambda. So to prove it, as B is a positive definite matrix, there exists a real non-singular matrix H transpose B H is equal to I. So since A is a real symmetric matrix, then this means that H transpose AH is also a real symmetric matrix. Therefore, there will exist a real orthogonal matrix K such that K transpose H transpose AH into K is equal to K inverse H transpose AHK, and this is a diagonal matrix which is denoted by this. So here lambda 1, lambda 2, lambda n are the characteristic roots of this particular matrix, that is this one, and these are therefore real. So if P can be written to be equal to HK, we are considering it that way, then the matrices H and K are real, so P is also real. Therefore, P transpose BP is equal to HK transpose BHK, that is K transpose H transpose BHK is equal to K transpose, this was equal to the identity matrix if you recall from here. So this is equal to K transpose IK, which will give us I, identity matrix, and P transpose AP is equal to HK transpose A into HK. This can be written as, on opening this bracket and grouping these terms together, we get K transpose H transpose AHK. So this will be equal to K inverse H transpose AHK, and this portion is equal to this diagonal matrix. Now, if P transpose A minus lambda BP is equal to P transpose A minus lambda P transpose BP, so that means that we subtract lambda into identity, that is lambda, from each of these terms. So that will give us this value over here. Therefore, P transpose A minus lambda B into P, if you remember the equation, so this comes out to be this value. And this can be written as in this form on expanding. So from here we get the value as this being equal to 0. Now since P is non-singular, therefore P transpose is equal, this the value of this determinant of P will not be equal to 0. Therefore, the determinant of A minus lambda B will be equal to 0, which are all necessarily real. And a corollary also exists for this theorem, which states that if X transpose AX and X transpose BX be two real quadratic forms, then there exists a real non-singular linear transformation X is equal to PY, which transforms the given forms to lambda y1 square plus lambda y2 square up till lambda yn square and y1 square plus y2 square and until adding up to yn square respectively, where lambda 1, lambda 2 and lambda n are all the characteristic roots of this equation. This can also be proven from the above theorem as P transpose AP is equal to a diagonal matrix and P transpose BP is equal to 1. So that's all from me for today. Thank you for watching. If you like the video, please share and subscribe.